Hi-ho! Here we are again. Impulse. Dun dun dun. Cool stuff. You can't talk about momentum without talking about impulse. Take a look at the picture of the golf ball. It's a real picture, as far as I know. Just like any ball, a golf ball will get smashed in on the side that you hit it. Realize you're hitting that ball pretty hard. Think about why that is. You're hitting this with some force over some period of time. Basically, by causing the ball to compress, the time is increased. And when you do that, you get a very large impulse. And of course your units should make sense. It's a Newton second or kilogram meter per second. Sounds a lot like momentum, and there's a reason for that. So what impulse is a force applied over some period of time. Keep that in mind. So let's do a real quick calculation. A soccer ball is kicked with a force of 150 newtons for a time of 0.1 seconds. What's the impulse? Well, I is equal to F times T. F is 150. Time is 0.1. So the impulse must be 15 Newton seconds. All right, let's try the next thing. Think about this. If we apply a force to something, imagine, if you will, pushing. In fact, go ahead and try that. Push on something. Won't you change its momentum? Remember, momentum is mass times velocity. You're not changing its mass, but you are changing. So mass times a change in velocity. You're changing its velocity. So a force produces a change in momentum. And likewise, if we apply a force for a very long period of time, we're going to change that momentum, well, quite a bit. So we have, looks like force and time, right? Either one of those, you apply a force, you apply it for some period of time, you end up changing the momentum. Put them together, and what do you got? Look at that. Remember, F times T is impulse, and delta P, delta means change, P is momentum. Well, momentum is, as we set up here, it's a mass times a change in velocity. From that, we can create a very large relationship. But first off, let's think about this. If I push off a boat, let's develop this concept. If I push off a boat, what experiences the most force? So here I am, right? I'm standing on a boat. I'm going to go this way. I push off the boat goes the other way. Remember Newton's third law? Who experiences the most force? That's right, they're equal and opposite. So no one does, they're equal. What about the greatest impulse? If you're smart, you'll pause right now and think about what impulse is. Okay, we're back. Here we go. Impulse is a force over some period of time. Who experiences more force? None of them. So this doesn't change. If I touch something for 1 second, isn't it touching me back for 1 second? So isn't the time the same as well? Therefore, the impulse is the same as well. They're equal. So who has the greatest change in momentum? If you remember from before, that impulse, the force times time, is equal to the change in momentum. So again, it's equal as well. So this relationship can be written as such. We know impulse is force times time. We know if we want to change the momentum, we're going to end up changing the velocity of an object. And we know if we exert that force per time, we're going to change momentum as well. So everything's equal to everything else. Makes it that much easier. Keep this in mind. This is the #1 formula you're going to be using. So we have this anxious hockey stick. It's going to strike a puck with a mass of 0.3 kilograms. And it's going to strike it with a force of 300 newtons. The collision only lasts 0.8 seconds. What's the velocity? Oh, we know it initially had a velocity of 0. What's the velocity it ends with? So that sounds like we're looking for a change. So how do you do this? Very simply, take that big formula that we had, m delta v equals a change in momentum equals impulse equals force times time. Let's check off the things we know. Let's see. We know a mass. We know a mass. We know a force. We know a force. We know a time. We know a time. We're trying to find a change in velocity. So it looks like we want m delta v equals force times time. That's how we choose our formula. Mass is 0.3. The velocity is some unknown. We're solving for that. The force is 300. The time is 0.8. And solve for x. And you will find your change in velocity. And we know it started at 0, so you'll find that velocity at which it leaves the stick. So let's put it together in a kind of a qualitative. Instead of using numbers, let's talk about the qualities of this happening. We can have a car striking a haystack as shown, or we can have that same car with that same momentum coming in, mass times velocity, striking a brick wall. Think about what's happening here. Who gets hurt? I hope you said the one striking the brick wall. Think about what's happening. Think about how that mass times velocity, or the change in momentum that's going to occur, because both times are going to come to a stop. Think about how that relates to the impulse, or force times time. Who experiences? Let me scratch that. Which one takes the longest to come to a stop? Of course, the haystack. The time is very large. You hit the brick wall, you come to a stop very quickly. So this is the same, and this is the side that we're changing up. So to keep things balanced, if this becomes very large, that must be very small, and vice versa. So here we had a very small time, and so you get a very, very large force. Here we had a large time, therefore the force is very small. You don't get hurt. This situation is akin to why an airbag saves your life. Put it in the realm of sports. What happens? You know, a boxer knows not to just leave his face there. When he gets hit, he moves backward. He does that so he can increase the time. He rides with the punch. And so we know the momentum of that punch, at least the change in momentum, is going to equal the force times time. If he increases that time by 4 times, he's going to decrease the force by 4 times. That fist coming in, it's not changing. Regardless what he does, that guy's hitting him as hard as he can. You can think of baseball. What do? You try to extend the time of contact with the ball and the bat. Right? You follow through. Let's backtrack to Newton's third law again. We have a bully hitting Calvin with 100 newtons of force. How much force does Calvin's face hit the bully's hand? Hopefully you're saying 100 newtons. The forces are equal and opposite. Why bring this up? Because it has everything to do with this idea of impulse and how it relates to momentum. So let's think about our relationship here. Our change in momentum equals mass times a change in velocity equals impulse equals force times time. So how does the change momentum of an object relate to the following? So how does the change in momentum relate to the impulse? Oh, look at that. They're equal. How about the mass times its change in velocity? Well, that is the change in momentum. What about the force times time? Again, they are equal. So they're all equal. And that should make sense. Because when you push on something, it pushes back with the same amount. When you touch something, it touches you for the same amount of time. So for both objects, the impulse is the same on each, which means the change in momentum is the same on each. And there you have it. If you have two identical cars coming to a stop, one does it in half the time. What can you say about the force? Think back to hitting that brick wall. A sad excuse for a car here. What do? You decrease the time. Remember, the momentum of that car is going to be the same whether it hits a wall or a haystack. Decrease the time, you increase the force. So if you have half the time, you're going to have twice the force. Lastly, what about bouncing? Think about what happens when something bounces, right? Impulse is force times time. What happens when you bounce? Think of an object. Here it comes. It's going to come. It's going to hit the ground, right? The ground has to bring it to a stop. So in other words, there's force number one. And then the ground does what? It pushes it back up. There's force number two. In other words, when it comes to impulses, which is force times time, you increased the force when you bounce because you had to push twice. Therefore, the impulse is greater. If you want a nice review chart of this relationship, here you go. I'll let you read it yourself.